Okay, let's look at an example now about how to do biasing and how to find Q point and also the DC load line. And in this example, you see a circuit very similar to what you had earlier, except that in this one you have slightly a little bit more complicated emitter circuit right here. You see, we'll see why it is. So, but for the time being, it's pretty much the same thing. So in this circuit you have the potential divider biasing, as you see here. So the potential divider RA and RB basically divides the VCC, so that's the potential divider biasing. And in this circuit, if you forget about this capacitor right now, you have an emitter resistor, which is the feedback resistor that you have in the emitter, and the rest of it is pretty much the same. You have the RC connected to the VCC, and RC is connected to the collector of the NPN transistor, and the signal is fed through the base, and the output is taken from the collector, right? So some information is given about this. The signal input is very small, so Vs is 12 millivolts, which is fed through an input capacitance of 100 microfarads. For the BJT, the on voltage, the forward drop of the base emitter diode is 0.7 volts, and the beta, the current gain, is 50. So what we are supposed to do in this is basically to find the Q point. In other words, we need to find what VCE and IC are at Q point, VCEQ, ICQ. And also we need to draw the load line. So what is load line? It's basically a relationship between IC and VCE. It's a function of, so some mx, x is VCE plus c. So this is like y is equal to mx plus c. So what we have to find out is the slope and the intercept, right? So we need to get an expression similar to this. So this is what we are, our aim is at this point. What AC load line is, we'll look at after that. All right, so let's get started here. So initially what we are going to do, so is the DC analysis. So DC analysis. In this, we want to find the Q point. In other words, we want to find the Q point. It's VCE, IC, VCEQ, ICQ. Okay, so the step one here in doing this is basically, now what we have in this circuit is a circuit which has some capacitors. So this is a general circuit, but when you are about to do a DC analysis, you need to get this circuit into the DC form. So we need to find the DC equivalent circuit. And how are we going to do this? Now, you know, in order to do this, if you so DC condition is what? DC condition means the frequency omega is equal to 0. Okay, so you know the capacitors. For a capacitor, what is its steady state, what is its impedance? XC. So this is a capacitor like this. A capacitor XC is equal to 1 over J omega C, where omega is the operational frequency in radians per second and C is the capacitance. Now when omega is equal to 0, my XC becomes infinity. Now if by any chance if we had an inductor, Now in this circuit we don't have inductors, but in general we can have inductors as passive elements. So if that is the case, you know the inductance, the impedance of an inductor is j omega L. In which case at omega equals to 0, my xl becomes 0. So what this is, omega xc is equal to infinity means this is an open circuit, and this is a closed or short circuit. Okay, so the first thing that you do is, when you have a circuit like this, you open circuit to get the DC equivalent circuit. Open circuit the capacitors and short circuit the inductors. Okay, so this is what we are going to do for our circuit. So if you look at this circuit, I'm going to open circuit this capacitor here. I'm going to open circuit this capacitor and this capacitor. So if I open circuit this, basically there is no connection here, so it is broken from here, and there is this capacitive part right here is also not there. So therefore all you have is RE1 plus RE2 here. So let me draw this circuit once again. If I draw that circuit, what you'll end up is with this RC and then you have the bias circuit. This is all you will have. Plus VCC 10 volts, and this is the circuit that we will be ending up. This is RA, this is RB, this one RC, RE1, RE2. That's my, you take the output from the, so this is V out. So now this is the DC. So let me say this is V out, only DC component. Okay, all these are DC quantities. So the first thing that we need to is basically find the IB, the current, but to find IB, you cannot directly find it, so you need to simplify this circuit. What did we do earlier? We used the Thevenin's equivalent circuit of the bias circuit. So this is what we are going to do again. So then the next thing what we do is find the Thevenin's equivalent circuit of the bias circuit. So what is my bias circuit? I have, this is my bias circuit. This is my bias circuit. So you have plus 10, this VCC, RA and RP, both 56K, 56 kilo ohms resistors, 56. Okay, so this is my, so I need to convert this into something like this. So this is RTH and this is VTH. What are these values? This is what we are going to find out. Okay, this is not hard to find. So VTH is easy. VTH is the open circuit voltage at base. So this is B. This is collector and this is emitter. VTH is equal to, so this is, it's very simple to find VTH. It's the potential divider. The RA and RB acts like a potential divider. So voltage B, or the VTH, open circuit voltage, is basically equals RB over RA plus RB times VCC. So what is this? 56K divided by 56K plus 56K times 10. This is half, so this is 5 volts, easy. Then to find RTH is the same as open circuit voltage divided by short circuit current for this circuit. So what is open circuit voltage? Open circuit voltage is the same as VTH, and so this is VTH. Okay, what is this? Short circuit current. So to find the short circuit current, what you will have is, if you short circuit this, in other words, you short circuit this, the path of the current would be like this, right? So the current path will be like this. So there is no involvement of this. So my I short circuit is equal to VCC divided by RA. So those are the only elements. So this is the only resistor that you have in my path. Okay, so that's 10 divided by RA, 56K. So therefore my RTH is equal to 5 volts VTH divided by 10 times 56K. 10 divided by 56K. So therefore this is 28K. And you will see that this is actually equal to RA parallel RB. Okay, so in general, so in this case, if RA and RB are equal, you will have half of the value, but otherwise it will be like that. Okay, so we know now the two quantities that we want for the biasing circuit, RTH and VTH. The next thing that we need to do is to find the DC quantities. Okay, so let me draw the DC equivalent circuit now with the bias circuit replaced with its Thevenin equivalent circuit. So you have the 10 volts, the RC, the transistor, and you have the resistors. And here you connect this to the Thevenin equivalent circuit represented by this RTH and VTH. This is plus VCC, RC, RE1 and RE2. So this is my new circuit where VTH is 10 volts, RTH is 28K, VCC is 10 volts, oh sorry, this is 5 volts, VTH is 5 volts, RC is 10K, RE1 is 240 ohms, and RE2 is 20 kilo ohms. So this is all we have. Now to find my quantities, I apply the Kirchhoff's voltage law to the base emitter loop. Kirchhoff's voltage law to base emitter loop, because I want to find IB. So what are the voltages that we have in here? So you have the currents IB, basically you can say IBQ also. This is IE and this is IC, and the voltages we have VBE, capital VBE, and VCE. So for the base emitter loop, this loop here, what are the voltages I have? I have voltage here across these two resistors. This is IE times RE1 plus RE2. This voltage VBE is also there, and this voltage, which is RTH times IB, and this voltage VTH. So if I write the equations, Kirchhoff's voltage law, VTH is equal to RTH times IB plus VBE plus IE times RE1 plus RE2. So 5 is equal to 28K IB plus 0.7 volts plus IE plus RE1 RE2 is 20.24 kilo ohms. So this is my new expression. I can simplify this if necessary, but before that, let me express IE in terms of IB. You know, IC is equal to beta times IB, and IE is equal to IC plus IB. So therefore, this is equal to 1 plus beta times IB. So this IC is equal to 50 times IB. This is 51 times IB. Okay. So if we continue with exact values, I can write the above equation as 5. So if I subtract 0.7 from 5, this will be 4.3 equals to IB times 28K plus 20.24K times IE. IE is 51, right? So I can say this is 51 times that. So that's that. So IB basically is 4.3 volts divided by 28K plus 20.24K times 51. Now if you want to find the exact value of this expression, you will see that this value is equal to 20.24 times 51 plus 28. Okay, so this is 1, and this is 1 over that times 4.3. That will be 4.06 microamperes. That will be my IB exactly. But as engineers, sometimes we do not really care about infinite precision. Now we care more about how easy it is to find, and we sometimes make approximations. Say for example, in this expression, we have this expression, you have 28K plus 20.24K times 51. Now when it comes to 20.24K, this is as good as 20K, because you know, if you look at the resistors, mostly they are 5% resistors. A resistor value can actually vary within 5% plus or minus. So 20K within plus or minus 5K is, it can actually be 1K. So it could be 21 or 19. So therefore this 0.24K, it doesn't really make much of a difference if you really look at the error that can be there in 20k. So therefore you can, for all practical purposes, you can consider this as 20k. For 51 also, 50 and 51 just point, it's just 2%, so you can consider this as 50 also, right? So 50 times 20k is like 1000k. With compared to 1000k, if you take 28k, again it is very small value, so therefore it's less than 3%. So therefore, for the first approximation, this looks like it's approximately equal to 4.3 microamperes. So to find that, you don't need a calculator, right? It's just you can do without it. So even this is good enough. So if you know that the actual value is this is only, it's the difference between this and that is just less than 6%. So it's up to you, depending on your application. 6% is not a big deal. So if necessary, you can say this is roughly 4.3 microamperes. Even that would not make much of a error. Okay, but if you want to be more accurate, you can relax. You can be more stringent as necessary, or maybe you can just consider only the 28k. So let's say this whole thing can be approximated to 1028k instead of 1000k, which would give you a value which is roughly about 4.18 microamperes. Again, it's not exact, but you see it, right? The trend is that if you say this is about 4.1 microamperes, this is more than enough. So okay, so it's in the range of 4.1 microamperes. So that's good enough for our calculation. You can go with whatever you want. So let's stick to one value here. Let's take this value as my final value. So anything is fine. This is fine, this is fine, this is fine, this is fine, but as long as you state your assumptions. Okay, so assuming these resistors are 5%, a rough value of 4.1 milliamperes is good enough. So let's say it's about that much. So okay, so note that your life can be made easy by making some sensible assumptions. So the important thing is you make sensible assumptions without affecting the accuracy much. So the accuracy is not going to be affected much. Within 10% is reasonable in our calculations, so we can do that. Also, remember that resistors are 5% resistors most of the time, so therefore by making these assumptions, we are not really compromising the accuracy. Even though if you go with the nominal values of the resistors to find the exact value, it may not be correct. Okay, so therefore the values that you get by making sensible assumptions are not really off by too much. Okay, now we know the IB. So IB is equal to 4.1 microamperes. Let's say this is our final value that we choose. So therefore, what is IC? So this is basically the IBQ, the quiescent current, because these are the DC conditions. So what is IC is equal to beta IB, which is equal to 50 times IB, which is equal to roughly about 2.05 milliamperes. So you can say this is about 2 milliamperes even. That should be fine. 2.01 milliamperes, 0.5 milliamperes. Oh, sorry, this is not 205 microamperes. I'm sorry. So this should be so 50 times 4.1 microamperes is equal to 205 microamperes. That's my ICQ. Okay, even if you go with the accurate value, it will not be off by too much. It will be very close to that. And what is my IEQ? So this is my ICQ also. Okay, ICQ is one of the quantities that we need. IEQ, which is IE, which is 51 times IB, which is roughly about 50 IB, that is also equal to 205 microamperes. So if you want to go, if you want to really go with the 51, this value would be 209 microamperes, which is good enough. Okay, so that's that. Okay, so we know the values here. Now this is the important value that we want. Okay, IE. So ICQ is equal to 205 microamperes. So this is one of the important quantities that we need. The next thing that we need to do is basically to find VCE. Okay, so to find VCE, we apply Kirchhoff's voltage law to the output loop, or CE loop, or output loop. So do you have in the output loop? So this output loop is basically what we need is this loop over here. Okay, so in that loop, what are the voltages we have? We have the same voltage here, and then we have VCE, and then we have ICRC, which is equal to VCC. Okay, so those are the quantities that will come in my equation. So let me write it down. VCC is equal to IE RE1 plus RE2 plus VCE plus ICRC. Again, going with the same assumptions, we can say, so if you write this exactly, it will be 10 volts is equal to IE is basically 209 microamperes times 20.24K plus VCE plus 205 micro times 10K. Okay, so this is the exact equation, so from which you can find VCE, but this is roughly about 205 microamperes, so we can combine terms, and this is about 20K. Okay, so my value will be VCE is roughly about 10 minus 205 micro times 20K plus 10K. So 20K comes from here, 10K comes from here, so that's basically the value. So this value will be 30K times 205. This will be 30 times 205 is equal to, so 10 minus 6.15. So VCE is roughly about 3.85 volts. Correct? Let's see. 6.15, 3.85. Okay, so that's my VCE, and that's equal to my VCEQ. So therefore my VCEQ equals to 3.85. So I know my Q point now. Q point is equal to 3.85 volts and 205 microamperes. This is one of the things that I was supposed to find. Okay, so even if you make this exact, it won't be much different from this, maybe within 5 or 10% of this answer. Okay, so the Q point is this. Now the next part of this is basically to find the draw the DC load line. Okay, so now the next is draw the DC load line. Okay, so how do you do that? Load line is derived by applying the Kirchhoff's voltage law to the output circuit, which we already did to find VCE. So because we need a relationship between IC and VCE to draw output characteristics. So we already have that expression. So we need a relationship between VCE and IC so that we can draw it on the output characteristics of the BJT. Okay, so we already have this expression, which is VCC is equal to, I'm going to write IC instead of IE because they are equal. IC times 10K plus 20K plus VCE. Okay, roughly. So therefore IC is equal to minus VCE divided by 30K plus VCC divided by 30K. So what do we have here? Minus VCE over 30K plus 10 over 30K. So this is about 330 microamperes. This is 330. It's roughly 0.33 milliamperes or 333 microamperes. Okay, so I can now draw the relationship because I have a relationship similar to what so I see. So this is like y equals mx plus c, where m is minus 1 over 30k and c is 0.333 milliamperes. Okay, so let me draw the characteristics. This is VCE, this is IC. I have the characteristic curves already given, and we know there's a saturation region and a cutoff region. Okay, this is cutoff, this is saturation. Okay, so my load line, so in this is about 330 microamperes, 333 microamperes, and the y-intercept is 10 volts. The VCC, you can easily get it from the above equation by equating IC equal to 0. So this is my load line. That's my load line, DC load line. Now let's say this is my 2 microamperes, 3 micro. So okay, so let's say this is my 4 microamperes, and this is 2 microamperes, something like that. So if this is the case, where's my so this will be my Q point. It's about 0.1, 4.1 micro. Sorry, so this is 4.1 micro, so roughly 4.1 microamperes. So this will be 205 microamperes IC, and VCE is basically, what did you have for the VCE? 3.85 volts. So that's my DC load line. Okay, so these are IB values. So my IBQ is roughly this way. Okay, so this now the question now is this properly biased? Okay, is this properly biased? That is the question. Now to find that out, so we know if it can amplify the whole signal that we input, that is 12 millivolts peak to peak, 12 millivolts plus and minus, so peak voltage is 12 millivolts. If we can actually amplify it without any distortion, in other words going into a cutoff for saturation, we call this is properly biased. Now the question is whether it can. Now in order to actually figure that out, we actually need to draw the what is called AC load line. When the signals change, the signal change is not actually on the DC load line, but it will be on an AC load line. Why is it? We are going to discuss. Okay, and now in this circuit, the saturation point is roughly about 0.7 volts here, 0.5 volts, so 0.2 VCE set 0.2, and this is a very small current, so therefore it's very close to 10 volts, but could be 9.5 or something like that. Okay, let's say about 9.5 volts. So it's safe to have it. Can have this at 0.5. Let's say this is 0.5 volts, so that we know for sure it will not go into saturation if you choose these two regions. Okay, so now let's look at the AC load line. For the above circuit. Now when you are looking at the AC load line, you need to remember that we choose capacitors. There are two capacitors in this circuit, the input capacitor and the emitter bypass capacitor in the emitter circuit. Now when you choose these capacitors, obviously at whatever the capacitor you choose, they act as open circuits for DC voltage, DC voltages, because omega equals to 0. So 1 over j omega C becomes infinity. But depending on your actual working frequency, typically the lowest frequency that you are working at. Let's say if you are using this for an audio application, typically the lower frequency could be 20 hertz or 50 hertz, around that range, tens of hertz, even 100 hertz sometimes, depending on your fidelity. So let's say it's 50 hertz or something. So when you are choosing these capacitors, you have to choose these capacitors in such a way that at the lowest frequency of this signal, input signal, these capacitors act as very low resistors or very low impedances or short circuits compared to the other elements in your circuit. Say for example, you have a resistor in the emitter circuit which is bypassed by a capacitor RE2, which is 20 kilo ohms. So the impedance posed by the capacitor should be way smaller than your resistance value. So typically a rule of thumb is about 1/10 or less, so that when current divide, just less than 1/10 of the current actually goes to the emitter resistor. So the almost all of it go to the capacitor, right? So in order to do this, we have to choose the capacitor if you are doing a design in such a way that the capacitance value across which you have across the resistor which you have placed the capacitor impedance should be at least 1/10 of the resistance of the resistor which bypasses. So that's what you need to do. So in that case, we can, again, assuming it's close enough, we assume these capacitors are short circuits. Similarly, if you were to use inductors, these inductors have to have a resistor that are way larger than your resistors. So something like, if you are using an inductor, it should look like an open circuit, at least 10 times as big as the series resistor that you may have. So therefore, what we do in obtaining the AC circuit, this is what we need in order to find the AC load line. You need to obtain what is called the AC equivalent circuit. So in obtaining the AC equivalent circuit, you short circuit capacitors and open circuit inductors. Why we can do it is, in designing, we choose inductors and capacitors to have at least tenfold either larger or smaller impedances when you choose inductors and capacitors. This is why you can do it. Okay, so let me give some notes. So now, in order to obtain the AC equivalent circuit, we short circuit the capacitors and open circuit the inductors because of the previous reason. And also, at AC conditions, DC voltage or current sources, they don't produce any AC signal. So therefore, they can be replaced by their internal resistances. Since DC voltage sources have very low internal resistances, and DC current sources have very high internal impedances. DC voltage sources have very low impedance, current sources have very high impedance. So therefore, when we draw the AC equivalent circuits, any DC voltage sources like the VCC, we short circuit because the internal resistance is almost zero. And if we had any DC current sources, not dependent current sources, any DC independent DC current sources, we just open circuit them. Okay, so this is what we do, and we use these rules to draw the AC circuit. So what do we end up with? Let's do that next. Okay, so let's draw the AC circuit. Draw the AC equivalent circuit. We know we have two open circuit inductors, short circuit capacitors, and short circuit DC circuits, DC voltage sources. So what do we end up with? We have the resistor here, we have the transistor, we have two resistors, but one of the resistors you have a capacitor which is bypassed with a circuit which is a short circuit. Okay, so that's my ground, and you have the bias circuit, and a short circuit here again, and you have the source. And also the DC voltage source has to be short circuited, replaced by its internal resistance. So this is basically what you have. So have RA, RB, RC, RE1, RE2, and this is what you have. So this obviously, this point then becomes the same as that, so you can actually put them together. So you see that RA and RB is connected between the base and the ground. RA is also connected at the base and through this part at ground. Okay, so therefore they are in parallel. So I can simplify this as you have the voltage source, and voltage source is also, by the way, connected between B and the ground. So therefore I have B here and the ground here, and you have RA and RB connected here. So this is still B, and then you have the BJT, you have the C here and E here, and obviously you can see this RE2 can be removed because there's a short circuit across it. So therefore you end up with only RE1 here. And what happens to C? C is again connected between the collector and ground. Okay, so therefore what you have here is RC here. And where do you look at the, where do you see the voltage? At V out. Okay, so this is my V out collector. So this is my AC circuit, this is my V in. That happens to be my AC equivalent circuit. Now to draw the AC load line, similar to what we did in the DC case, what we need is an expression between VCE, which is this. Now notice that I have used all simple letters to indicate that this is a purely AC signal, and the IC. Let me mark it as this. Okay, VCE, IC. So in order to obtain an expression for VCE and IC, I need to apply Kirchhoff's voltage law across the output loop like that. Okay, what are the voltages that you have there? So this is IC. That's a similar current will be flowing through this. This is IE, and this is IB. Okay, IE, which is equal to beta plus 1 times IB, which is roughly equal to, because beta is big, 50, right? It's roughly equal to beta times IB, which is equal to IC. So therefore IB and IC and IE are roughly equal. So I can, instead of using IE, I can use IC, because what we need is a relationship between IC and IB. So what are the voltages you have? You have this voltage, which is IE times RE1, and this is VCE, I have that, and I have this voltage, because the current flows from here to there, so the voltage is in the opposite direction, IC RC. Okay, so let me write the expression, the Kirchhoff's voltage law, apply Kirchhoff's voltage law to draw the AC load line. AC load line, apply Kirchhoff's voltage law to CE loop. Okay, so therefore I can write IERE1 plus VCE plus ICRC is equal to 0. There is no voltage. So therefore, if you make this roughly equal to RC, I can say IC, if this is roughly equal to IC. Okay, so I have IC RC, this is RE1 plus RC plus VCE is equal to 0. So therefore IC is equal to minus 1 over RC plus RE1 times VCE. So that is my expression. This describes my AC load line, because what we need is an expression between IC and VCE. You immediately notice that now you don't have an intercept. Okay, there is no plus C. So this is like y equals mx. This is y equals mx plus C is 0. What is m? M is equal to minus 1 over RC plus RE1. C is equal to 0. Okay, so therefore this load line, AC load line, is different from DC load line because of two reasons. In the DC load line you had RC, RE1 and RE2 in the expression, and the intercept C was equal to VCC divided by that total resistance in the collector and emitter circuit. Now here, so therefore both my intercept and the slope are different. What is my slope? My slope m is equal to minus 1 over RC is 10k plus RE1 is 0.24k, right, 240 ohms. So this is roughly about minus 10k, because 0.24 is less than 1%. Sorry, 10%. This is like 2.4% of my total resistance. So therefore it is too small. So we can assume this is about this much. So this is what we have. So if you go back to my original circuit, go back to, if I draw the go to the DC load line. So this is the green color one. The slope of this slope is equal to minus 1 over 30k. Now it is minus 1 over 10k AC load line. So should it be more steeper or less steeper? You'll see that if this is a negative slope, so therefore what you have is actually so let me draw this again to make it more clear. Okay, so let me draw the load line again. Now this time I am going to call it VCE, which is AC and DC both. Simple I, capital C, IC. Okay, so So this was the output characteristic. Now if you were to draw only the AC load line, it would go through the origin and it would have a slope of 1 over 10k. So it would look something like this. The slope, this is the AC. So this is actually not the AC load line, but according to, if you were to have VCE versus IC, all simple, then this is what it would look. The slope equals minus 1 over 10k. Okay. Now our DC load line was something like this. Something like that, and this was 4 microamperes IB. So this was something like 200.205 milliamperes and 3.85 volts. Now, so this is my AC, purely AC load line, and this is my, the green color one is the purely DC load line. But what we have is a combination of AC and DC. So what we need is IC is IC, simple C plus IC, whereas VCE is VCE plus capital VCE. AC part, this is the AC plus DC. So therefore, if I combine both, now you need to understand that the operating point, in other words, when the AC current is 0, the total current is at the Q point. Okay, at the Q point. So it is here. So therefore, we need to move this red line here. So what ends up happening, my total AC load line becomes something like this. This is my AC load line. This we call the AC load line, and it has to pass through the Q point. Okay, so this is the relationship between VCE and IC, the combination. The slope of this is minus 1 over 10k. Right, so that basically is what we have. Note that the slope is steeper. Okay, it's a less negative value. Negative value, which is more than minus 1 over 10th is greater than minus 1 over 30. Okay, right. So now the original question that we asked, is this properly biased? In order to answer that question, we need to know whether we can have this is 0.5, let's say, and this is 9.5, let's say. So we need to be able to have voltage swings that allows 12 millivolts. So during the 12 millivolts that we apply, it should not go into saturation or cutoff. Okay, if we can have that, this is called properly biased. Right, so this is basically the circuit that you have. Now, how do you find the whether it is properly biased? So you use this AC circuit. When you apply 12 millivolts value, you have to find what my currents are going to be, and then you can find IB, also you can find IC, and from that you can obtain the swing. Okay, so I'm not going to do it at this point, because in this question what is asked is just to find the DC and AC load lines. Okay, so this is basically what you have. Okay, so that concludes our example here, and also with that the section on biasing. I hope this part is clear, and I have uploaded the lecture notes also onto the Fields website. You can refer to that, and if you have any questions you can ask me. Thank you.